Hi, welcome back. I'm Tess Zhang. And over the 2 weeks from this week, I'd like to briefly introduce the basic concept of the reinforcement learning. And for this, I first start to introduce the dynamic programming model, and especially for the deterministic cases. And followed by the Markov chain for modeling the evolution of dynamical systems. And in the next week, I will introduce the Markov decision process, which reinforcement learning relies on. I note that, roughly speaking, the Markov decision process is kind of the mixture of the Markovian process, for example, Markov chain, with the dynamic programming. So that is the reason why I start to introduce those two concepts, dynamic programming and the Markov chain in advance. So and I will talk about the basic components and terms and solution approaches for the Markov decision process. And then finally, we'll discuss the basics of the reinforcement learning with its associated basic the algorithms. So in today's session, we'll briefly take a look at some basic terms and mechanisms of the dynamic programming models. All right, so since our discussion contains the inductive argument, so I'd like to start the discussion on the so-called mathematical inductions. All right, I believe most of you already learned this concept during the middle school. All right, so here is some general formulation of the mathematical inductions. So let P1, P2, and so on be the statement where the each may be true or false. To suppose that P1 is true, so P1 is true, and if Pn is true, then Pn plus 1 is true for all n, then all the statements of the Pn are all true. So let's take a look at the examples. So the statement Pn is given as like this. The sum of the 1 to the n is equal to 1n times n plus 1 divided by 2. Right, so we just apply this, the mathematical inductions. So in the first, we'd like to make sure that Pn is true. So let's say n is equal to 1. P1 is equal to 1. The left hand side is equal to 1, and the right hand side is 2, 1, 1 plus 1. So that means equal to 1. So 1 is equal to 1. So we can confirm that Pn is true, right? And let's assume that Pn is true. Then we'd like to make sure Pn plus 1 is also true, right? So what we can do is by adding n plus 1 to each of these equations. So the left side become 2. So I'd like to add n plus 1 on both sides. And that is equal to 2 n plus 1 plus n plus 1. Right? So this right hand side become 2 n plus 1 and n plus 2. So what we can say here is that is Pn plus 1 is 1, 2 plus up to n plus 1 is equal to 2 n plus 1 and n plus 2. So what we can say here is if Pn is true, then as we can see from the statement, Pn plus 1 is also true. So it follows from the principle of the mathematical inductions, then Pn is true for all n is greater than or equal to 1. Right? So I'd like to talk about, before moving on, I'd like to emphasize here is there is some recursable relationship between the Pn and Pn plus 1 as follows, right? So Pn plus 1 is equal to Pn plus n plus 1, right? So there is some recursive relationships between n plus 1 and Pn. All right. And we now talk about some of the major algorithmic paradigms. And greedy algorithm is one of the example of the algorithmic paradigms. So the algorithmic paradigm is a generic approach to algorithm design, right? And greedy algorithm takes the best you can get right now without regard for the future consequences. All right, so let's take a look at the example. So in this graph, we'd like to find out the shortest path from node 1 to node 5, right? And based on the greedy algorithm, we just choose the best one we can get from now without regard of future consequences. So you are currently in the node 1, and there is a 2 option to choose the next node to visit. So either 2 or 3, right? It takes 100 and it takes 30. And you'd like to find out the shortest path. So among the 2 choices, you will choose this route, right? 1 to 3, right? And you are currently on 3, and you have the 2 options to choose. So either 4 or either 5, and it takes 10 and it takes 60. So you may choose the shorter one. So that means you choose the 4 as a next node to visit, right? And then 4, you have 2 options to choose, either to go to the 2 or go to 5, right? And then it takes, let's say, 15 minutes, or it takes 15 minutes. So probably you choose the node 2 as a node to visit next. So you keep doing this, and that is the kind of the approach of the greedy algorithm, right? So as you see from these examples, the greedy algorithm builds up the solution incrementally, and then it optimizes the problem based on some local criterion at each step. Okay, so another example of the algorithmic paradigm is the divide and conquer algorithm. As you may guess from the name divide and conquers, so this algorithm breaks up a problem into the separable subproblems and solve each subproblem independently and combine the solution to the subproblem to build up the solution to the original problems. So we split the problem into these smaller problems and solve each smaller problem recursively, and then we combine the result from each smaller problems. So let's take a look at what the meaning of the recursively. So this smaller problem is still big to solve, and it is somehow difficult to tackle with the size. So the recursively means you split this smaller problem into even smaller problems, right? So you apply the same principle, same procedure we did for the bigger problems. Split the smaller problem into even smaller problem, and you solve even smaller problem recursively. And then we combine the result. And if this even smaller problem is difficult to solve, so what you can do, you just split the small problem into the tiny problems. And you apply the same thing, right? So if this procedure can be represented in this way, the tree. So given the original problem, you just split into the 2 subproblems, right? And this subproblem is difficult to solve. You just split the problem again, right? And then again and again. And what you can do, you just solve the small problem and then combine the result of this subproblem to build up to form a solution to the larger problem. And for this, you just combine the result from these 2 solutions and then build up use the combination of the 2 solutions as a solution for this problem, right? And then to get the solution for this subproblem, you just combine the result from this and this. So eventually, you can get the solution for the original problem. All right, so what is the dynamic programming? Dynamic programming looks similar to the divide and conquer algorithm because the original problem is broken up into these smaller problems. However, dynamic programming breaks up a problem into a series of the overlapping subproblems and then build up the solution to a larger and larger subproblems. So if you think about this is the whole problem, right? And divide and conquer algorithm divide the problem, break the problem into two subproblems as like this. And dynamic programming model, so here is the original problem. You try to break the problem into the series of the overlapping subproblems. That means a subproblem contains a smaller subproblem, and this smaller subproblem contains even smaller problem, and so on. So that is the kind of the dynamic programming has a structure of structure of the nesting, right? Nesting structures, right? In this one. So basically, the dynamic programming problem is supposed to have the same structure, but the size of problem is smaller. And we try to express this overlapping structure, nesting structure, by using the recursive equations. So the dynamic programming is a method of solving a complex problem by breaking them into the subproblems that can be solved by working backward from the last stage. So the last stage problem normally has the smallest subproblem. So in this case, suppose that original problem is expressed as this kind of nesting structures. So what we can do, we just solve the smallest subproblem, and by using this result, you solve the bigger problem, and then you get the solutions, and you solve this problem by using the result from this subproblem, and then you get the solutions, and then finally you solve the original problem by using the result of this subproblem. Right. So this dynamic programming was coined by the Richard Bellman, who described the dynamic programming as a way of solving the problems where you need to find the best decision one after another. So that is this some kind of sequential decision making. All right. So the dynamic programming, he named the class of the optimization problem, which find the decisions over time. So the dynamic means the over time, right? The making a decision over time. And programming means a planning, right? So dynamic programming means the planning over time. Okay, so in order to play with the dynamic programming, we need to consider so-called principle of optimality. The principle of optimality simply means the sub-solution of the optimal solution of the problem are the optimal solutions of each sub-problems. Right. So you may not understand what this means from the statement. So for better understanding on the concept of the principle of optimality, I'd like to introduce one examples. So let's consider a problem to find out the shortest path from node S to node D. And in that case, let's assume that the optimal solution pass by the node I. Then what can you say? What can you tell about the subpath from the S to I and then I to D on this optimal solutions? Probably this subpath from the S to I on the optimal solution must be the optimal solution to the problem finding the shortest path from node S to node I. Also, this subpath from the I to D in this optimal solution must be the optimal solution to the subproblem, finding the shortest path from the I to the D. Why? You can easily show by contradiction. So for example, so if this is not the shortest path from the node I to node D, that means you can find out the alternative path and which is shorter than this, right? So that means if you take a look at the original problem to find out the shortest path to the S to the D, and then this path must be shorter than this path, and that contradicts the assumption that this is the optimal solutions, right? So what we can say here is this subsolution of the optimal solution of the problem is the optimal solution for this subproblem and the subproblem, right? That is the meaning of the principle of optimality. And when we formulate the dynamic programming model, we rely on this principle of optimality. So the optimal, and we're going to take a look at the this statement. The optimal immediate decision depends on only the current state and not on the how you get here. So what does that mean is, so suppose that, so you are currently in the node I, and you'd like to make the decisions to decide the node to visit next. All right? So what this statement means is, when you make the optimal decision, you'd like to decide the optimal solution for given the node I, the decision does not depend on previous history about the state, what node you visited so far, and then what was your decision for each node, right? The only thing that affect the decision of finding the optimal node to visit next depends on the current state and then how many steps are remaining. Right. So unfortunately, the principle of optimality may not always hold. So let's take a look at the example. So if you take a look at this graph, we'd like to find out the longest path from the S to the D. You can easily identify the longest path from S to D as S to the 2, and 2 to 1, and 1 to D. And that is the longest path from node S to the node D. Well, let's take a look at this subproblem to find out the longest path from the node 1 to node D. If this problem hold the principle of optimality, so what I mean is, if the principle of optimality holds in this problem, this subsolution of the optimal solution of the original problem must be the optimal solution to this subproblem to find out the longest path from the node 1 to node D. Well, but you can easily see that the longest path from the node 1 to node D must be 1 to 2 and 2 to 5 instead of 1 to D directly. So from this example, we know that this longest path problem, longest path problem does not hold the principle of optimality, right? So in this problem, the principle of optimality is not satisfied. Okay, so I'd like to introduce some kind of basic component of the dynamic programming. So let us consider a dynamic system which moves through the sequence of the states. So we're going to talk about the definition of a state later on. The S1, S2, S2, S3, and so on at each time of the 1 through t. Right? So we're going to take a look at this graph. So given this current state, and there is the decision maker who make the decision of the A1, A0, and then that lead to the next state of the system. And then by observing the current state of the S1, decision maker make the decision of the A2, and that lead to the next state, S2, and so on. So we keep doing this in the system. So here is some basic component of dynamic programming. So every problem is divided into the stages or the decision epochs. So each time of the decision epoch, we make the decisions, right? So each stage requires the decisions. And the decision at one stage transform the state into the state in the next stage. So that means, each decision epoch, and the decision maker observe this system state and then make the decisions. And the decision transform the state to the next state in the next decision epoch. So the solution procedure is to find the optimal solution for every possible state. That is called the decision rule. So you need to find out the decision rule for every possible state. So that means in the decision rule state, what you need to make the decision for every state, right? And then you need to find out the decision rule for every stage. So the collection of the decision rule is called the policy, right? So when you make the decisions, you need to have some measures. In the dynamic programming model, there is a so-called the reward. The reward depends on the state and action, right? So when you for the given state, if you make some action, if you choose some actions, so that incurs some kind of reward. Reward can be positive or negative. And finally, in the dynamic programming model, there exists the recursive relationships that identify the optimal decisions for stage J, given that the state J plus 1 has already been solved. So because of these recursive relationships, this solution procedure often starts from the last stage and then walk backward. And the final stage must be solvable by itself. Okay, so let us revisit the dynamic system we have seen in the previous slide. And this dynamic system is characterized by the following two functions, ft and rt, right? Then ft specifies how this system of this dynamic system evolves over time. So ft is a function of the current state and then action, right? And this function specifies what state we're going to have in the next stage. So given this state, decision maker chooses the action AT, and that leads to the next state with a probability of 1. So that means you know for certain of the next state if given the state ST, you choose the action AT, right? So that is called the law of the motion, right? And then whenever decision maker chooses an action, there we need some criteria, decision making criteria. So in these cases, suppose that given the state xt, decision maker choose AT, the reward occurs. So that is specified by the function RT, right? So given this situation, given these two functions, the problem is to choose the sequences of the actions A0, A1 through AT minus 1, assuming that in the problem finishes at this time. In order to minimize the total cost over the given period or given time horizon t for given the initial state S0. So you try to start with the S0, and at each stage you choose then certain actions, and if for the given state, if you choose the action, that lead to the next state, right? And then whenever you choose a certain actions, certain reward or cost incurred, and basically we'd like to choose the sequence of these actions to minimize the total cost. And we need to think about how we're going to solve this problem. So let's think about the following, the idea. The choice of the present and future actions cannot possibly affect the past. That means, so given the current state, when you choose the action, this decision does not affected by the past, right? So how long it doesn't matter how you get to this current state. When you make the decision, optimal decision for this state, right? This decision only depends on the current state and then how many steps, how many stages are remaining. So based on this rationale, we can construct some kind of a subproblem. So at any time t, let us consider subproblem minimizing the total future cost. So ct plus 1 up to ct minus 1. So given this time horizons 1 through t, original problem is to find out the sequence of action to minimize the total cost over this whole time horizon. The subproblem consider the total cost from small t up to to the end. So if you consider this structures, it is natural to walk backward in time. In other words, let's think about, you try to find out the best actions to minimize the total cost over this time period, right? So that is the optimization problem. To find out AT plus 1 up to AT minus 1 to minimize this the total future cost over this time period. And that is equivalent to express in this way. Instead of finding the whole solution, you can walk backward from the last stage problem. So that means, in the last stage, you can immediately find out the optimal solutions. And by using this result, you can solve t minus 2 problem, and then you can walk backward. So that is based on these discussions, we can construct this kind of the recursive equations. So this total future cost from the period 2 to the end is equal to the minimum value of this immediate cost, right? Current state st, if you choose at, right? That is the kind of the immediate cost at the current stage t, plus if you think about the minimum future cost from the stage t plus 1 to the end. And you try to find out the at, then minimize the immediate cost and the minimum future cost, right? That must be the minimum future cost from t to the end. So we have some kind of the recursive relationships. So when you make the decision at the current stage, you need to consider not only the immediate impact, but also the future impact as well. And based on this recursive relationships, you need to solve this problem to get the this problem, to get the solution for this problem, right? So that means we work backward from the last stage problem, and then you just solve the you just walk backward in time to get the optimal solutions. So from this recursive relationship, you'd like to find out the optimal solutions. You are interested in solving. You are interested in finding out the solution of this, right? V1 star S0. Starting from the S0, you'd like to find out the minimum total cost from the period 1 to the end. Okay? So let us take a look at the example and then see how the so-called backward induction mechanism works. Okay, so we'd like to take a look at so-called the stagecoach problem. So in the stagecoach, this is a stagecoach, and in the stagecoach problem, there is a source and that destinations, and then there is some intermediate node, and it can be considered as a city. So you'd like to move from this city A to city J, right? There are some intermediate node, and you'd like to use a stagecoach to get to the final destination J from this initial node A, right? And this arc represents there is some possibility, there is some road from the city A to city B, and then it takes, let's say, 2 hours or 2 days, and so on, right? So that the number on the arc represents the distance for each city. All right. So we'd like to solve the problem by using the mechanism introduced before in the previous slide. So you'd like to walk backward from the last stage, backward in time. Okay. So we'd like to walk backward in time to solve the problem of finding the shortest path from the node A to node J, right? And one possibility you can do is you just identify all the path and then calculate how long it will take to get to the J from A. And then you enumerate all possible paths, and then you calculate the length of path, and then you compare it to each other, and then you can identify the shortest path. But instead of doing that, we try to walk backward in time to find out the optimal solution for this stagecoach problem. Right. In the stage 5, there is only one state, J, and J is the destination, so there is no decision to make, right? And we moved backward, this stage 4. In the stage 4, we are interested in finding the shortest path from the current node H or I to the J. So V4 star H means the shortest path, the length of the shortest path from the node H to the J. And V4 star I is the shortest path from the node I to node J. J is the final destination. Well, there is only one option, right? From H, there is only one path to get to J. And it requires the 3, right? And when it comes to node I to the J, it takes 4 days, right? So we can represent this in this way, right? For the given state, H and I, Okay? You choose the action, right? If you choose the action J. So for node H and I, you only have the one option. The action is one node to visit next, right? There is only one decision, one action. So that is a J. And it costs 3 and it costs 4. So the minimum should be 3 and 4 respectively. And the action to choose at the current state must be J. There is only one action available in this case. Let's move the backward, right? Let's move on to the backward, stage 3. So V3 star E means the length of the shortest path from the node E to the node J. And V3 star F means the length of the shortest path from the F to the J. And V3 star G means the shortest path from the node G to the node J. If you can see here, for the current node E, you have the two actions. You can go to either H or I. And for node F, you only have the two options to choose, either H or I. G, also same, right? And how we're going to calculate the cost of these, right? So here is the illustrations. So given this state, let's think about the state E, right? So if you choose H as a node to visit next, right? So it takes 1 day to get to the H, right? And you already calculate the length of the shortest path from H to J, right? H to J is equal to 3. So that comes a 3, right? So that is equal to 4. If you choose the I as a node to visit next, right? Oh, I'm sorry, there's a typo. There's an I, right? So the action is I, H or I. Right, so if you choose the I as a node to visit next, it takes 4 days to get to I from the node E, right? And then you already calculate the length of the shortest path from the I to J, right? Which is equal to 4. So you add 4, right? So in this case, 8. And you'd like to choose the shortest path, right? And you need to choose, either H or I as an action to choose. So you'd like to identify the shorter one. That means the 4 must be length of the shortest path from the E to the J. And your action you choose is H, right? You decide to go to H, right? And if you think about the F, so F, you have two options, right? H or I. So if you choose the H as an action for the current state F, the immediate cost is 6, right? It takes 6 days to get to H from the F. And then you already calculate the length of the shortest path from the H to J, which is equal to 3, right? So that is 9. On the other hand, from the F, you choose action I, then it takes 3 days. So 3 must be immediate cost or immediate reward. And you already calculate you have the information about the length of the shortest path from the I to J, which is 4. So you have 7 in total. So for given state F, if you choose H as an action, then the minimum total length from the F to J is 9. And if you choose action I for the current state F, then the length of the shortest path must be equal to 7. And you'd like to choose the minimum one, right? So that is equal to 7. And the optimal action to choose for the current state F is equal to J. So you can do same thing for the G as well, right? All right, so far we solve up to the stage 4 and 3. So we move on to stage 2. In the stage 2, right, so we are interested in the value of a V star B, V2 star C, and V2 star D. The definition of this is the length of the shortest path from the node B to the node J. Okay, and at the node B, we have 3 possible actions to choose. Go to either E, F, or G, right? So if you decide to choose E, the immediate cost is equal to 7. So it takes 7 days to get to E, right? And then you already calculate the minimum, the length of the shortest path for the E to J, which is specified by V3 star E, right? So you need to add 7 plus that. The 7 plus V3 star E means the length of the shortest path from B to J if you choose E as a next node to visit, right? And then you need to also consider the F as an action to choose. So if you choose F as an action, you need to incur the immediate cost as a 4. So it takes 4 days to get to the F from B, and then you already calculate the shortest path from the F to J. That is represented by V3 star F. Right? If you choose G as an action for the given state B, it takes 6 days, and then you already calculate how long it will take from the G to J if you take the shortest path. So that is equal to 3 star a G. Right? And you are interested in finding the minimum of these 3 options. So I can express this one by using this table. So for the B, you choose E, F, G, right? And the 7, if you choose E, 4 if you choose F, and 6 if you choose G. And then 4, 7, 6 comes from the table from the previous slide. So 4 represent V3 star E. F represent V3 star F. 6 represent V3 star G. Right? So you can calculate, this is 11, this is 11, 12. You'd like to choose the minimum one. So that is equal to 11. So 11 means the length of the shortest path from the B to J must be 11. And from B, that 11 can be attained if you choose the E or F as an action. So when it comes to C, right? C, if you have 3 actions available. So either go to E, either go to F or G. So if you go to E as a node to visit next, it incurs 3, and then 4 must be equal to V3 star E, right? So you can do the same thing, E and 4. If you choose the action F and G respectively. So 2 and 4 are immediate the cost, and then you need to consider the the future impact as well. So that is 7, 9, 10. You are interested in finding the shortest one. That is equal to 7. So 7 means the length of the shortest path from the C to J, and the 7 can be attained if you choose the action E from the stage C, right? So you can do same thing for the D as well. And then finally, action A. So suppose that in the stage 1, that is the something we are interested in the original problem. You'd like to find out the length of the shortest path from the A to J, right? So in the current state A, there are 3 actions available: B, C, and D, right? B, C, and D. And if you choose B as an action to choose, and then 2 as an immediate cost, and we already calculate the length of the shortest path from the B to J, which is you need to refer to V2 star B, which is equal to 11. So 11 comes from here, right? And that is equal to 13. So from A, if you go to B, then the shortest path from the A to J, the length of the shortest path from the A to J, if you choose the action B as an action to choose, then it takes the 13 days, right? Let's say if you decide to go to C from A. So immediate cost is 4, it takes 4 days. And then from the C to J, it takes 7 days, right? It's 7 days. So that is equal to 11, right? If you go to D as a next node to visit, it takes 3 days to get to D, and it takes 8 days from D to J. So that is equal to 11. So you are interested in the minimum cost, right? So the length of the shortest path from the A to J is equal to 11. And 11 can be attained either if you choose either C or D, where if you are currently in this state A. So basically, by doing so, by working backward in time, we can find out the optimal solutions, which is equal to 11 in this case. And initially, you start the journey from A to C or A to D. And in the C, if you choose C, the next node will be the E, right? So go to E. So something like that, right? So by these tables, you can find out the optimal solutions as well. All right, so I'd like to briefly wrap up what we've discussed in this session. Right, so dynamic programming simplifies a problem by breaking into the simpler overlapping subproblems, and that is represented in the recursive manner, right? And we talk about the stage or decision epoch, state, action, reward or cost, and we also talk about the decision rule, right? And the policy, and we also talk about the value functions. Value function is represented through the recursive equations. And when the time horizon is finite, we just simply walk backward in time. So that is called the backward inductions. So we take a look at one simple example to see how the backward induction work, right? So that's it for today. So thank you.